Thank you. I wanted to give you, you're going to get a much larger presentation later today from Mike Seablom, excuse me, who's going to be talking in, who's going to be talking more broadly about the specifics of our science program. So I wanted to sort of just lay a much broader discussion of what it is we're trying to do at NASA and how technology is so critical to accomplishing that. These are the 5 areas of science that we cover at NASA, which you're probably very familiar with. First of all, studying the sun, which has such huge fundamental challenges in the fact that the bulk of what we do in terms of heliophysics is really trying to monitor the sun and provide early warning of solar flares or coronal mass ejections that could be headed towards the Earth. In terms of a fundamental understanding of how the sun works, we're actually still pretty far from that, which is exciting from a scientific point of view because there's so much work to be done in terms of understanding the sun and in terms of sending humans out beyond the Earth's magnetic field where they're subjected to radiation from solar storms. It's a critical area in terms of being able to improve our ability to forecast and to understand the environment outside of the Earth's magnetic field as we send humans out into areas that are much more dangerous. In terms of astrophysics, I know David touched on this, but when I go out and talk to school kids, I always tell them they all need to become planetary scientists like me. Of course, I'm just trying to recruit small children, but on the other hand, you know, when you consider the fact that 30 years ago when I was in school, when many of you were in school, you know, we had 9 planets. We now have thousands of planets, largely due to the Kepler Space Telescope. But when you consider what's gonna happen over the next 3 to 4 years with the transiting exoplanet survey satellite, which we estimate will detect 1 habitable planet a month, in terms of the James Webb Space Telescope, which will look at the atmospheres of some of those planets around other stars, the ability of scientists to not just study the planets of this solar system, but to study planets in other solar systems is increasingly amazing to me, but in terms of scientifically, it's a huge growing field. It's going to change the way we look at how planetary systems form. It already is. It's going to change the way we look at planetary climates and how they change over time. And indeed, just the whole issue of how hard it is to get a habitable planet is something that in the next 10 to 15 years is actually within our grasp. And this is incredibly exciting. And that's why I encourage kids to go into it, not just because I think we should have more planetary scientists. When we talk, as we do at NASA a lot these days, about sending humans to Mars, because that really is our overriding goal in terms of moving humans out beyond low Earth orbit where we have been for so long, so successfully, moving humans out first to the vicinity of the moon and then on to Mars within the next 20 years is something that NASA is really using as an overarching driving goal. And it actually fits into the science that we do because getting back to those extrasolar planets, thinking about habitability, trying to understand how ubiquitous life is in the universe starts in our own solar system. So when we say we want to send humans to Mars, a large part of that is because we need humans on the surface of Mars doing science, looking at a lot of rocks, because that's what it's going to take to actually determine, did life evolve on Mars? What are the characteristics of that life? And how can we use that information to understand life better here on this planet, but also then think about those thousands of planets that exist that Kepler has found, but actually in reality it's billions of planets out there in our galaxy, in the universe, in terms of how likely is it that there is life, which we think is highly likely, but then getting to that point of thinking about complex life, how likely is complex life beyond our own solar system? So Mars is really key to answering that question. The conditions on Mars were very similar to those on the early Earth, so life should have evolved there. If it didn't, that's actually also scientifically interesting, not not as exciting, but still scientifically interesting, and again, has something to tell us about the likelihood of habitability beyond our own solar system. So getting to Mars, which a lot of people say, oh, we can do that in 2 or 3 years. I strongly believe that we need to keep doing the research that we're doing on the International Space Station every day to get humans ready to go to Mars. We have made huge progress in trying to keep humans healthy in space in terms of bone density loss, in terms of muscle wasting. There's a lot of the health factors that we have found mitigations for that work pretty well. There's others that we still have work left to do on. For example, the intracranial pressure rise, reducing the peripheral vision of some of the astronauts is still something we need to do more research on. There's still a lot with isolation, mental health research, with research on immune system function, research on nutrition, and of course then how that plays into some of the other side effects from microgravity effects is still something we have work left to do. So we think it's really critical to have the ISS as a platform at least through 2024 to then get ready to move out to what will be basically the test habitat for the vehicle that will take us to Mars, where humans can survive for 1+ year. Probably the chief technology driver in that area is really the life support systems. Scrubbing CO2 out of the atmosphere on the space station, having a reliable way to process urine. These are small things to us, but, just think about going to Mars with 6 people in a broken toilet. It doesn't really fly, so to speak. So it goes all the way from those mundane systems on the ISS to the really important systems removing CO2 and producing oxygen that have to work reliably. And so that's a whole technology area that I think is really interesting, pushing for new technologies that give you a whole new system, maybe a more efficient system, versus reliability, which is really critical. So that research that we're doing every day on the ISS, especially focused around the life support systems to then get us ready to move humans out to the lunar vicinity and then on to Mars within the next 15 years, it is an exciting area of research. Planetary, we're looking forward to the Juno encounter this summer with Jupiter, and then OSIRIS-REx launching in September, so it's going to be a busy year in planetary in terms of new missions. And of course, we're also somewhat in mourning, well, at least I am. I'm a member of the Cassini radar team, which has been studying Saturn so amazingly for over a decade. Cassini will actually end its mission next year when we crash the spacecraft into Saturn. But an amazing legacy of findings, and again, back to the life issue in terms of looking at the moons of Saturn from the subsurface ocean of Enceladus to the geysers, the lakes on Titan, and intriguing environments for studying life. And then, of course, there's the outer solar system beyond Saturn, Uranus, Neptune, where we really have so much still left to learn. So lots of excitement in planetary. And I left out Europa, which, of course, we're planning a mission to Europa right now. And again, the subsurface ocean on Europa, an extremely likely target for potential habitability, and we'd like to go find out. So we've selected the instruments for a Europa mission that will fly hopefully in the early 2020s, and we're right now studying a lander to accompany, actually it probably won't accompany, it would fly later, a lander to actually get down on the surface of Europa and try to analyze its surface. And then, of course, the most important planet, and that's our own, where we have 19 missions right now, studying this planet, trying to understand climate change, but increasingly over the next decade, we're going to see how can we use space-based data of this planet to help us with mitigating climate change effects. Because frankly, at this point, we're walking into higher sea levels, increased levels of storms, effects on agriculture around the globe, an increasing number of effects that, again, over the next 10 to 15 years, no matter what we do about our carbon emissions, are going to increasingly become part of our lives. And space-based data is really poised to help us with so many of those effects of climate change that we're going to be seeing happening. And of course, the ongoing role of making sure we have the best models that we do and that we're providing the best information to show how the planet is changing. So that's a broad overview of science, and I know Mike's going to talk a lot more later about how we're looking at technology in these areas. And most of you in this room probably know all that science that I was just talking about. We get our priorities through the National Academy of Sciences, which is looking at the overall, they look at each of these different areas of science that you see in each of these little stovepiped areas up here, and set the priorities. So the science community is the one who comes forward and says, here are the big missions you should do because these are the big measurements we need in order to really move science forward in any of these 5 areas. So we really do rely on the Academy to set the science priorities for the coming decade. And the Earth Science Decadal has just begun a few months ago, and the Astrophysics Decadal will be the next one to queue up in a few years. So those are a constant ongoing process that really helps us decide what's the important thing to do next. So I've got about 4 minutes left, so if you guys have any questions about science priorities, I'd be happy to answer. I know. No questions. Okay.
Daryl Shook from Honeywell. I understand that you referred to the ISS as a platform for building and establishing deep space mitigation factors. How do you reconcile the issue of perhaps the approach taken on ISS might not work due to the weight or the power consumption of any of the other, I'm sure you're aware of some of the approaches on ISS may not work in a deep space mission. What can you say about that as far as how you're developing technologies to go farther?
Right, and you know, that's the kind of thing that makes us feel that this next step of a deep space habitat out in the vicinity of the moon is important and why we need to get moving on it. And so it's why you're hearing at NASA talking a lot about it, because the ISS is a great platform for really testing out certain technologies, but it's not the same as a deep space habitat. That's going to be much smaller. It's going to have much more, as I was saying, much more reliable systems. It's going to be smaller, different mass, different power requirements. So doing PowerPoints of it, doing studies is one thing, but we need to go try it, and we need to put it out in deep space, and we need to work on it, you know, and we need to have humans on it breathing and doing all the things that humans do to make sure it's a reliable system before we actually send it on that 8 months to Mars, 8 months back. You need to really have a shakedown of that system to make sure it's reliable. And that's why we think the deep space habitat is so incredibly important. That's why the BAA, the Broad Area Announcement, went out, and we're happy to be working with multiple partners on looking at what that deep space habitat should look like. My aim is that we're never losing focus that what that is not a space station around the moon. It is the test vehicle for the vehicle that will get humans to Mars. And so I think, and those are 2 different things. And so we need to make really sure what is at the top of what the requirements for that are. Are we really driving that system in that direction? Because to me, that's the criticality. It's not a space station at the moon. It's a practicing to go to Mars. But that being said, we can still push how we use the ISS every day as far as it can go as a system in terms of saying, how can we really use this unique platform as much as we can to get ready to go to Mars?